All right, so I think nothing really new. I think you know when the exam is, and then your lab number 4 has been released. Just make sure you submit in time and also learn the stuff, right? So I think just steady. We only got like a small number of topics just to cover for refinement number 2. That'll be the last refinement, but I'll rather be a little bit slower on covering each one of them because some of them, especially the second and third one, are quite tricky. So I'll rather just cover them slowly. But today, we're going to do something we're kind of familiar with about invariant preservation, just introduce a little bit more inference rule, and we'll see how that goes. If we can finish earlier, we finish earlier. I don't really plan to be very ambitious in terms of coverage. We are pretty good in the pace, right? Just go slowly. And then I think on Thursday, I'll try my best to see if I can release the exam guide, including some instruction about the data sheets. And also I can even post the sample exam question already, right? I can give them to you. You can take a look. And then I'll send some polling pretty soon, just about when you guys might prefer to have an in-person review session after the last day of the class. Okay, I'll get in touch with you. Okay, maybe later, maybe tomorrow evening or early on Thursday. Okay, either way. All right, so very quick recap. Okay. Before that, any questions? Yeah.
Yeah, 2 questions. First question, is that the reference paper in the scope of the exam?
That one there?
Yeah.
I would. Is it? Sorry. Sorry about that. Yeah, that paper there. Well, you know, yeah, it's really hard to answer, right? Because I know if I say no, then you may not read it. But if I say yes, but you might be upset if I don't put any question on the exam, right? If you read it. How about this? I'll put it this way. The tabular expressions there, I'm being very honest. I definitely wouldn't ask you details about that paper because many of the stuff there are beyond the scope for this course. On the one hand, on the other hand, I might take a look at the tabular tables over there. As an example, I might try to form some basis of my questioning exam. It's possible. I'm just saying possible. I'm not saying for sure. But I would say just good for you to maybe skim through and find some useful information about tables method. That's really the intention.
Thank you for the answer for the second question is that what is the percentage of students that finish the course evaluation?
I don't think you guys really, you know, since you asked, I gotta check, right? I think I checked on Sunday. I think there might be some small increase after that. Let's take a look. Oh, sorry. Let me just do that quickly. Sorry about that. Okay, so let's now check it and give you the precise answer. 091. There we go. Okay, so I think for us, it is 62%. You know, I would say that's really good. Yeah, I mean, how about this? I will definitely read the feedback. Hopefully nobody is going to benefit from that, I'm pretty sure, right? Nope, everybody want to pass, right? You don't want to take this course again. Nope, no way, right? But, you know, I really appreciate everybody's feedback. You know, I think I'll definitely try to help you the best I can for your exam. Anyway, okay, so that's all your question, right?
Yeah.
Yeah, no worries. Yeah, I want to be sure, okay? No worries. Okay, very quick recap, okay? So last time we spoke about relative deadlock freedom. It's a lot of discussion here in this page. I wouldn't repeat, but I think there's something to point out. When you talk about guard strengthening, you're only talking about old events because for every old event, you got a concrete version. You also got a corresponding abstract version. So you're really talking about the concrete guard implies an abstract guard, only the old events. On the other hand, when you study for relative deadlock freedom, the disjunction over here is about the disjunction of all the abstract guards over here, right? On the other hand, the concrete guards over here is about the old events together with the new event guard as well. Intuitively, since you got guards from more events, in some way your system should be less deadlock free in some way. All right, keep that intuition there, and then try to go over the different scenario about the relative delta freedom being provable versus unprovable, and go over the scenario. Okay, that's something you will have to spend some time, and you can ask me again, maybe during the review session or at Stuttgart office hour. All right, so take a look at this one here. And then we talk about the proof obligation itself. It's very straightforward to formulate it. Okay, you just got abstract art over here, concrete art, everything here. And of course, you got the extra disjunction about IL in, IL out, right? So usually shouldn't be too difficult to really discharge the relative delta freedom. And the proof for you, okay, for exercise. You can definitely find a solution on the slides as well. And that's a summary about the first refinement. And for the second refinement, we're going to go for a similar roadmap. So today, we're going to look at invariant preservation today, right? We're going to see how the invariant preservation is going to fail. We're going to look into it and try to see what we can do to fix it, right? And then we got guard strengthening, other things as well, life lock, and also relative delta freedom. So that's something we'll look at a little bit more closely on Thursday and also next Tuesday, the last class. Okay. Again, one thing just to remind you before I forget. If you look at the lecture site, I put the inference road over here. I believe these are all the 4 sets of inference road you will need for the exam. All right, so these are everything you will need. How many you want to put in the data sheets is completely up to you. You can choose what you like. Okay, so you can choose, and you can take a screenshot if you want to handwrite. If you want to type it out, no problem. Okay. Okay, good. And then also I put out all the refinement proof also for the second refinement here as well. So you got everything, right? Everything's here. Right. And after next Tuesday, I also put all the slides and also all the iPad notes together as a document. So I'll try to do that maybe Wednesday morning, since we have no more school, so maybe Wednesday. I'll reach out to you once it is done. It's not difficult for me. I just need to spend some time. Okay, and then we spoke about the second refinements, right? For the second refinement, we talk about something called super precision, right? So we're basically reusing everything, all the variable A, B, and C from M1. And then we are trying to do in M2, we try to introduce another 2 new variables, MLTL, traffic light for the mainland, ILTL, the traffic light for the island. So these are the 2 extra variables we are introducing. Okay, today we'll look a little bit more into them to see what kind of invariants we want to preserve. We'll see. Okay, that's something we'll get into today. And then we try to figure out 2 very important invariants. Given that the MLTL over here is green, what does that mean? That means the A plus B should be less than the upper cap, D. And also, there should be nothing going this way, right? That's exactly what we're saying. On the other hand, for ILTL over here is green, so it's kind of the opposite. We want to make sure there's no car coming this way. A should be 0. And also, there should be at least 1 car that will go from the island to the bridge, right? So that's also something we spoke about last time. Okay, straightforward. Any questions? Okay. So I would say for you, when you study the exam, you want to, of course, you may put down some maybe proof or any proof that you don't feel exactly comfortable that you can actually refer to during the exam. But I would say pay more attention to the pattern that we are justifying. For example, when I ask you about whether a particular guard should be necessary, how do you formulate the corresponding sequence to show that it is necessary? Now, you want to kind of pay more attention to that kind of justification. Because if I give you another model, I simply put out a guard, ask you, would it be necessary to put this guard? That's something you want to be able to justify. Okay. Anyway, all right. All right, for today, I want to start with this little trace over here. Because in order for us to really come up with the guards for the events, we need to somehow understand the trace. There will be some fundamental assumption we have to clarify as well. Okay, let's talk about this simple trace. It's kind of fun to see how that will represent. So let's say we have some initialization for the system. Let's say we got init right here. Okay. After initialization, let's say both traffic lights are red. So you can think about this traffic light here is red. I don't know why. Okay. So this one here is red as well. Oh, sorry, I chose the wrong pen. That's why. There we go. So let's say this is red and this is red. Okay, in the beginning. All right. And we're going to talk about the occurrences of 1, 2, 3, 4, 5, and 6. 6 events. Okay, we're going to look at them to see how things will do. And then I'm going to explain to you somehow about how the design of guards will be a little bit different for this refinement here. But there's some good intuition behind that. Okay, so let me just label them. So let me say MLT, there are 2 events with traffic lights. It will be this one here, number 1, and this will be the number 4, right? The 4th event in the trace. Okay, I'll just use the same color. Also, we got ML out right here, number 2, and also IL out, number 5. Okay, I also got number 3 and also number 6. Okay, we're going to talk about all these 6 events together. Okay, specifically for ML out and also IL out. Here and also here. So these 2 are more like simulating the driver's behavior. Okay, let me write it down first and I'll explain to you what that really means. So these 2 events are really simulating the driver's behavior. Which is, they only look at the traffic light. If that's red, they stop. If that's green, they go. All right? They only try to look at the traffic lights. The traffic light either here or the traffic light here. All right? And then the first one is about in order for the driver to really go through, let's say from the mainland to the bridge, this light here must be turned green, first of all, right? So the first event in the trace is going to be the occurrence of MLTL green. So MLTL green. Okay, so this is number 1. When that happens, that means rather than being red, it's now going to be green. All right? There will be some guard we have to design for this particular event. Let's say as soon as it turns green, so now the driver, if they want to get through, the ML out event is going to happen. So number 2 is going to be ML out. Number 2, ML out. Okay, of course, when the car actually goes through from mainland to the island, we're going to increment this, right? Making sure. Also, we got to make sure before we do that, A plus B must be strictly less than D. Right? That's something we know pretty well too. As soon as the driver actually approaches to the island, then the ILN event is going to happen. This one here. Okay, so this will be the 3rd event in the sequence. Okay, so the driver will just leave from the bridge to the island. So this will be number 3, IL in. Okay, good. There might be a bunch of cars in the island. In this case, just one car, right? We're talking about just one single car traveling in the circle. So the IL in, and then let's say now the driver should really wait for this light here to really turn green. They should wait, right? At the same time, this one should be turned red, right? So let's say we do that. So that means this one is going to turn green. At the same time, this one here, of course, is going to turn back to red again. Okay, like that. All right. That way, we are going to have the events over here. This will be number 4, ILTL green. ILTL green. Events. So think about when this event happened, it's going to turn this one to be green, at the same time turn this one to be red. It's more like a sensor, like a system operation at the same time. Okay, as soon as this light is green, now the driver can really follow the traffic light and move on to the bridge if they want to leave the island. So that one there, it would be 5th events. So this will be right here. Okay. So that would be number 5, IL out. And when they actually get to the verge of the bridge between the bridge and the mainland, so now number 6 will be ML in. They go back to the mainland. Okay, so again, these 2 events are very special. ML out over here and IL out here. I'm going to write it down here. So when you actually study for this refinement here, you want to compare how the ML out is designed in the previous 2 model, M0 and M1. And this one here, we try to move it more realistic towards the real world in the following sense. So when we talk about A, B, and C, so these are more like a computer variables. It is something that the system will keep track. So for me as a driver, if I want to know whether or not I should really go onto the bridge, do I care if what A and B, C's are? I don't. I only care about whether the light is green. That's all I care, right? That's really the kind of the reality we want to reflect in the model. Okay, I'll write it down. Okay, so this is why we're going to design the guards in a different way in this model. I want to clarify that before we do that. So A, B, and C are computer variables. Which means the drivers should not access their value. They should not have access. Drivers have no access. Well, they simply don't care. Have no access to their values. No access. So consequently, the two driver-centric events is going to be ML out and also IL out. Number 3 and number 5. ML out and also IL out. For these two events, as you will see later in the guards, we only have to just worry about whether the light is green or red. That's all we care. All right? So the drivers should only be concerned about the traffic lights color, whether it's red or green. Okay, that's all they care. All right, let me do a little bit more comparison. Okay, let's now compare M1 and M2. Okay, let's split it over here. So first of all, let's talk about M1, and I'll talk about M2 over here. Let's start with M1. If you recall, M1 was the first refinements, where we also got A, B, and C. So that was the first refinements, where we got A, B, and C, but we don't have the two traffic lights. Okay, over there, we actually got mainland, ML. And then we got a bridge right here. Since we don't really have the traffic lights, so we only got ML out. We don't have ILTL green. That was only introduced in M2. Right? Let's revisit what we did over there. Over there, for ML out, ML out. Okay. That one there, I can just copy it right here. The guard for that is simply saying A plus B should be strictly less than D. It should be limited. And also, the traffic this way should be 0. And also, C should be equal to 0. That's what we had in M1. So now what's going to happen is you will see that this guard over here, that's to do with A, B, and C. They are not going to be part of the MLR guard anymore because those will be what the driver should really obey, which will be the traffic lights, right? Okay, so what you will see in M2 is something like this. In M2, so we still got our ML over here, and we still got our bridge, but now we got a new variable, for example, traffic lights. So this traffic light here is MLTL. So now we got both the ML out and also we got ILTL green. We got two events right now. Let's write it down and I'll show you how the guard has been shifted. Okay, so what we got is we got ML out as before, ML out. And also we got this new events, ILTL green. That's a new events. So that's ILTL green. Okay, so now let's talk about the guards for these two events. As simple as this. What used to be considered as the guard for ML out in refinement number 1 will be considered as the enabling condition for turning the light to be green. Once we turn the light to be green, the driver can just go. Okay, so think about this guard over here will be shifted. So this guard over here will be shifted to the guard right here. okay, as you will see. On the other hand, for ML out, over here, the guard has been made very simple. Just about IL, TL equals green. As soon as this is the case, which will depend on this, it will turn the light to be green. In that case, the driver can go through. Okay, so in some way, we're splitting the ML out into two events, ML out here and ILTL green. That's what you can think about. Okay? Okay, let me make one more remark and see if you got any questions. If not, we can go ahead and fix the model. I mean to write out the guard. So M2 over here, you can think about we have split the ML out in M1 to number 1, IL, TL, green. Also, the ML out. We still got ML out. It's just that it's a more realistic perception about what a driver should do. They only look at the traffic lights. Any questions? All good? Okay. So what we should do now is let's now go to the model and put out the guards. Okay. So what we'll do is will be very straightforward. Okay. First of all, let's look at the ML out and IL out. So again, let me remind you very quickly, ML out is supposed to be just going this way, right? ML out. And IL out here will be right here. So now, what should be the guard? The guard should be just about the driver observing the lights. So this one here, in order for the driver to really go through, this light here got to be green. All right? IL, TL equals green. So if you compare this guard here in M2 versus ML out guard in M1, they're different. But as I explained, we try to reflect more reality about driver obeying the traffic lights. And we shift the original guard from ML out in M1 into ILTL green, which you will see next page. Question?
Isn't the variable name supposed to be MLTL?
MLTL, yeah, I agree. I definitely thought that way. Thank you. There we go. Thank you. ML, TL, green. And also symmetrically, this IL out, we got to make sure this light here should be green. IL, TL should be equal to green. And some of you might be thinking ahead already. Shouldn't we have to make sure that these two lights are not green at the same time? Because if they are green at the same time, cars might just go from both ways. I agree with you. That's something we'll see today. Okay, we'll get there. Okay, I'll make a note over here. So you have to make sure for these two events, they should not be enabled at the same time. Otherwise, you might just get car going here and going here at the same time, right? Okay, I'll put it here. In order for these events not to be enabled at the same time. IL, TL, and ML, TL cannot be green. Cannot be green at the same time. That's something we'll see. All right. Just look ahead for later. Cannot be green at the same time. Okay. All right. So these are the two events, and you can look at action. Action should be no surprise. Okay. So now let's look at the traffic light. When should we turn this light to be green, and when should we turn this light to be green? Right. So what will be the condition? So now, if you look at that, MLTL green, you just turn it to be green. ILTL green, you just turn it to be green. Right. Just right here. But now we want to look at the guard over here. Okay? You will see that there are two parts of the guard. Okay? Part number one, you want to make sure when I want to turn this particular light, okay, let me show to you just one way. if I want to turn this one here to be green, I got to be sure at the moment this one here is already red. Otherwise, I shouldn't even do it. All right? So that's why part number 1 over here, you're going to see that. So number 1, IL, TL will be red. Oh, I beg your pardon. This is something we'll cover a little bit later. I just got it slightly wrong. Okay. Just for now, for simplicity, all we got to make sure is, okay. So what I just mentioned is also valid. We also want to make sure this one here must be red, but there's something that will be ensured in other proof obligation. We'll see that. Okay. I'll mention that later. Okay. As simple as when I want to turn this one to be green, you got to make sure before you turn that to be green, to start with, this one here must be red. Otherwise, if that's already green, you shouldn't turn that green again. Okay, so if that's already green, red, you can turn that into be green. Okay, that's what I meant. So this will be MLTL equals red. Right? Symmetrically, if I want to turn ILTL to be green, I better make sure I don't turn that green twice in a row. Okay, I want to make sure that particular light is also red. ILTL equals red. Okay, like that. That's the first thing we want to do. Simple one. And other than that, we want to make sure we actually, when we turn this on, we want to make sure A plus B should be limited. And also there should be nothing coming this way. Right? That's kind of the guard we're kind of expecting. And no surprise. Like what we just described. I'll write it down first. It's going to be A plus B less than D, and also C equals 0. Okay? And this part here, you can double check. This part here is exactly the abstract guard for ML out in M1. So this is the abstract guard of ML out in M1. So if you recall what we just said earlier, what used to be the guard right here for ML out, we kind of shift that to this ILTL green guard over here. Right? Good. And similarly, over here for part 2, we are just going to put over here the abstract guard for IL out. Okay, let me write it down first and then I'll annotate. So that one is going to be B larger than 0. We got at least one card from the island. And also this side here should be 0. Okay. So this one here is the abstract guard for IL out. So this is the abstract guard of IL out in M1. Right? Any questions? So logically, we have already dealt with what the guard should be already in M1. It's just that now we have shifted what used to be ML out, IL out to the MLTL green and ILTL green because we want to reflect more reality. Question?
Quick question: how these new guards don't break the invariant 3 and 4?
They will break actually. It's a very good. That you raised the right question, right? As soon as we are done with the event, we want to ask, are we going to preserve the invariant, especially for invariant 2, 3, and 2, 4? That's really the 2 we want to preserve. It turns out the model as is not going to preserve them. So we're going to see. So once we find that unprovable sequence, we're going to decide how to fix the model and the whole workflow again. Yeah. So right now the model is not perfect just yet, not correct. So we're going to fix it. Okay. All right. Questions so far? Okay. Okay, let's now try to go a little bit further. Okay, I think I will just do a few more. Maybe some inference row and we'll take a break. Okay. So we're done with the events. So let's now try to formulate invariant preservation. Okay. So I just did one of them, right? We got ML out, which it will be here. And also invariant 2, 4, which is right here. Oh, let me highlight it. So we talk about ML out, which is the events right here. Okay? And also we talk about invariant 2, 4, which is this invariant right here. Okay? So how do we formulate invariant preservation? Right? That's something we did earlier, so we don't need to repeat from scratch. Just remember, you got to put in axiom invariant, abstract invariant, concrete invariant, and also the concrete guard, in which case it will be this particular guard. Right? So let me show you where you can find it in the actual sequence. So MLTL green, you can see that MLTL green. Right? You can see that's right here at the end. Right? That's a guard. Apart from that, everything is something we did earlier. Okay? So this part here just correspond to right here. Oh, you see exactly the annotation I put right here. Okay? You can go over that. And for this part here, it's going to be the invariant we want to preserve. In this case, we want to preserve invariant 2, 4. Invariant 2, 4. So if you look at that, the before-after predicates for ML out, it only changes A. So that means only A prime will be equal to A plus 1. Everything else stay the same, right? So that's why you can think about this A here is going to be turned into A prime. So that's why you see A plus 1 over here. Okay, I'll make it bigger. That's why you can see A plus 1 over here. So that one there really corresponds to A prime. Other than that, everything B prime equals B, C prime equals C, etc. All right? All right, so this one here, if you want to practice again, feel free, but that one is really something we did earlier, so we don't need to spend time on that. And you can also give a try on a different proof obligation, different sequence. Okay. Let's just go over some inference rule and then we'll take a short break. So these, I believe this will be the last set of rules, I believe. Okay. Okay. So we got 3 of them. All right. They're not difficult to understand. There's something, I'm pretty sure you have seen them in 1090. Let's start with the first one. This one saying we got imprecation on the left of the turnstile. All right. So we got imprecation on the left. So imprecation right here. Okay? But this one here is really saying if you got imprecation here and also the antecedents of the imprecation is also one of the hypotheses. In that way, you can simply say Q, the consequent. Okay? Let me highlight to you. We are basically saying if you got something like this as the hypothesis, you can then just put this as a hypothesis. We're basically saying this one here can be simplified to Q, given that the antecedent is true. I'm pretty sure I've seen that before. It's called modus ponens. Okay? That's not write it down. Okay? But the name is not something you need to memorize, right? You can just, I think for our course, just remember this one is implication L. So this one here is called modus ponens. Modus ponens. So if you got P and also P implies Q, that one there will just give you Q. If you got P, the antecedents and also the implication, and you can just get the Q, the consequent. Okay, as easy as that. We'll see one example after the break in one of the proof. Okay, that's one. And the second one there is saying if we got implication on the right of the turnstile, right here, that one is saying you can simply put the antecedents to the left of the turnstile. Okay? That is, I'll get there. I'll get to you. So if you got implication here as the goal, you can simply extract the antecedents as a new hypothesis and keep the consequence as the simple goal you want to prove. Question?
Yeah, sorry. So I was wondering about modus ponens.
Yeah.
Like P implies Q implies Q. Right?
Yeah.
So then why do we keep the P in the hypothesis?
Okay, good question. You can think about what we're doing here is we are more trying to simplify this particular term over here. We used to get P implies Q, but also we're given that P is also true. So we can simply simplify the orange part over here to just the Q. That's what we're doing. But the P there will still keep it handy just in case you want it. But if you don't want it, you can just use monotonicity to drop it. Yeah. Good. Okay, Q right here. Good. All right, so for this one here, it's something we also did, I think a little bit earlier. It's called shunting, but I'll just write it down. So this one here is going to be something like this. If I got H and P implies Q, all right? This is just equivalent to H implies P implies Q. If I got nested implication, I can simply combine the antecedents and then use a conjunction between them. That's what I'm doing, all right? Okay, so think about, we got H here, we got P here. So now we can combine them using conjunction rather than nested. Okay. All right, final one. This is something we actually did in one of the theorems in the math review lecture. Can you kind of recall what this is? If we got not P, turnstile Q, we can actually do not Q, turnstile P. Yeah, contrapositive, exactly. Very nice, okay? So let's see why, okay? So if you think about this one here can be formulated as just this one for the turnstile. It's like a not Q implies P. And this one here is like a not P implies Q, right? Contrapositive, you simply move this one to here with the negation. Also move this one here to put the negation. Not P, it's going to be P. All right? So you can definitely use contrapositive in the inference rule as well. All right? Questions? Okay? All right. So I would suggest we take a break, and then after the break, we just want to look at the invariant preservation sequence, how the proof will go, and it's unprovable, I can tell you, and then we'll try to interpret that and see how we can fix it. All right, let's take a short break. All right, so we're not going to really build the sequence proof from scratch. That's something you definitely can also try to go over yourself. I'm going to just point out some places because there are certain implication rule application, there's certain inference rule application that we just learned. So we can take a look, quick look. Okay, so there are actually two sequences we want to prove. So before the break, we spoke about this one here, and also one of them for exercise, right? We're going to look at these two, okay, these two. Okay, so this is one of them right here. This is the second one, all right? These are the two. They are kind of arguing in a very similar way, so we put them together, okay? I just want to show you one of the few steps, few steps in the proof. Okay, first of all, let's isolate this one here. Okay, so let's look at this one here, and also this one here. Okay, let's look at these two sequence, and we claim that we are trying to use implication R. Okay, that's what we claim to do. Okay, so what apparently you can see there is an implication here, right? That's what we have. So what we can do is, you can think about, let me just undo, now make it more explicit for you. You can think about, we have some implication over here, all right, right here. According to the rule for implication R, that one there we just spoke about before the break. It is this one here. If we got implication here, we can move the antecedent as a new hypothesis. That's what we can do. In order to prove this particular sequence where the implication is to the right of the turnstile, it would be sufficient to prove this particular sequence where the P has been moved as a new hypothesis. That's how you interpret that. All right, good. So what we do is we try to move this guy here, ILTL green, to right here. That's what we're doing. Okay, so we're just applying the inference rule. So you can think about this one here, which is antecedents. So now we can move them to as a new hypothesis right here. Okay, that's one step. Okay, another step we can do is implication L. Okay, so now we're going to look at this one here. Let's look at this one here. And also this one here, right here. And we claim that to really connect these two sequences, we can use implication L. That means the implication happens somewhere to the left of the turnstile. And there's only one, right here. Okay, right here. Okay? You can see that's the implication. Okay? So let's now make it explicit. You can see this is the implication. Let's now revisit what the implication L rule says. If you go back here, implication L is right here. All right? So that one is saying if you got some implication here, also the antecedents of the implication happen to be also a hypothesis. In that way, you can simply turn this implication here, just simplify it to its goal. That's what we have. So in this case, how do we simplify? I got this particular implication here. Now I'm going to look to see, do I also have the antecedent being a separate hypothesis? I do. Right here. Agree? Okay. So now you can now try to, I will just highlight this one here and also this one here, right? You can see I got these two. Given these two, I can now cancel this implication here. I can only leave out this consequence because the antecedent is guaranteed to be true as a hypothesis. All right. So after applying this, you can see that I got this one here, but I still have this original one. I don't really drop it. If you want to drop it, you can feel free to use monotonicity later, but you can. All right. So you can think about right here, I still got ILTL green there, but the consequence over here is now standing alone right here. Mode exponents. Okay. Yeah, so these are the two rules I want to show you very quickly. That's something we just learned a few minutes ago. Okay? And as you go over this particular proof sequence, it turns out there will be one branch that's unprovable right here. Right here. Okay, I'm going to zoom out. I'm going to zoom in very soon. Okay? This is one unprovable sequence for this sequence. And if you look at another one for another event, you will end up having another unprovable sequence that look just the same. So it turns out they are rooted from the same issue. Okay? So this one here is going to be just that as well. Okay? So the same unprovable sequence appear twice in our proof obligation for preserving the invariance. So now let's look at them more closely, okay, quickly. And then we'll see how we can interpret that. Okay? So I'm going to write it out here. So the unprovable, so the outstanding unprovable sequence looks like this. So here we have three hypotheses. We have the green is not equal to the red. And also we got ML, TL equals green. We got the other traffic light, IL, TL equals green. And it's saying that the model, it is saying the model is able to offer you this hypothesis, which is already not quite right. How can these two lights be green at the same time, right? And that one there, turnstile, 1 equals 0. So it turns out this represents a contradictory scenario, which we'll see. Well, I'll visualize that to you a little bit later. Okay? Let's just recall a little bit quickly. Okay? I'm going to put it here. If you look at invariant 2, 3, okay, and also you look at invariants 2, 4, okay, so those two will have these two being the antecedents. I'll show you right away. Okay, let's go back. So invariant 2, 3 and also invariant 2, 4. So we know that when MLTL green is actually the case, it should be that C is equal to 0, right? And also when ILTL is green, A should be equal to 0, right? So these two. Okay, so let's now just remember this, and then I'll put it there, right? That's something you can cross-reference later when you study. Invariant 2-3 tells me that if this is true, that means A should be equal to 0. Oh, I beg your pardon, C should be equal to 0. C should be equal to 0. And also, invariant 2-4 tells me that if this is true, then A should be equal to 0. That's what we know by the invariance. Okay? But it turns out that the current model actually allows A to be equal to 1 and C equals 1 when both lights are green, which is a very bizarre scenario, but the current model allows that, turns out. Okay? It's a contradictory scenario. We want to convince ourselves it's really possible, and then we'll see how we can fix it. Okay? Yeah, so don't really read too much into this. This is just telling you it is possible for your model to have these two lights to be green at the same time. So that's not good. We know. Okay? So let's now try to visualize the scenario. And if you look at the other provable sequence, it will be the same. So you can do the similar interpretation as we just did. Okay? And let's now try to look at one example trace very quickly. Okay? Again, that's the unprovable sequence we just looked at, just that one. Okay? And this is a trace after initialization with the maximum number of cars just being 2. Okay? So we set the MLTL to be green, so this will be green. The other one is still red. Well, initially both are red. Oh, let me just try to maybe highlights, easier for you to see. Initially, both are red. This is red, this is red. And then after MLTL green, we're going to turn this one to be green, and that one there remains to be red, which is fine. Okay? And then we're going to do ML out, which is going to increment A to be 1. Awesome. And we're going to do IL in, which is going to increment the car in the island to be 1. Right? And also ILTL green, which is the traffic light on the island side. So that one there is actually going to turn ILTL green also to be green. Also. All right? So now you can see both lights are green at the same time. Okay? That's how we end up in a scenario where both lights are green. So it's possible. So this is possible. So this is possible for both lights to be green. Okay? But even worse, because at the moment, you only got just one car in the island. You don't have any crash just yet. But let's go on a little bit. Okay? So now if you do IL out over here, you're going to have just C equals 1, because now the car goes to the bridge. You can think about the C over here is really a car heading to mainland. One more. The final events, ML out. This one here is because MLTL is actually green. The driver will just follow. It's going to increment A to be 1. So this means we have one car heading to the island. So now one car heading to the mainland, one car heading to the island, so now we have a crash. So the current model is not good enough. All right? So that's kind of the contradiction we have. Okay? So one more thing to really show to you. Okay? you can think about right here. We said earlier, ILTL equals green. So this means the C, oh, sorry, not C. When ILTL, this traffic light here, is actually green, so that implies A must be equal to 0, right? However, when you look at this one here, ILTL is actually green, but A is not 0. So if you look at this part here, A equals 0, and then if you want to conjoin them together, A equals 1 and A equals 0 should be false. You got contradiction. Okay? So now let me just write this scenario out specifically. Okay, just this one here. It's a little bit subtle here, but it's just going to take some time to see exactly how that happened, right? I'll try to give you all the information so when you study for that, you will see. Okay? So now in this particular state, so number one, we know that ILTL is green. ILTL is green. Number two, based on invariance to 4. Invariant to 4 entails that A should be equal to 0. Number 3, but at this state, A is equal to 1. But A is equal to 1. So now we got a contradiction. A equals 0 and A equal to 1. Together, we got false. Contradiction. All right? So now, how should we fix it? Right? We'll see later that we may have to somehow put some extra guard, etc. But to really somehow really make this on the right direction, we just want to add one invariant to make sure, we want to make sure these two lights are not really green at the same time. We want to make sure that happens first. And there might be some additional things we want to add, which will be next, the next class on Thursday. Today we'll just do one fix. There will be multiple fixes we have to do. Okay? So now based on this, so there will be multiple fixes. Fix number one, we want to add a new invariance. Okay? We want to make sure this should not be possible. Should not be allowed. Should not be allowed. All right? Let's do a little bit of derivation, because if you think about intuitively, how is this going to work? Okay, let's do a little bit of derivation quickly. Okay, I want to make sure this it cannot be true at the same time. I want to make sure not the case. MLTL equals green. Also, ILTL equals green. This is something I don't really want to allow. You can actually put this one here as a new invariant. That's okay. Logically, that's correct. But it's not so easy for you to really use that invariant for further proof, because you got negation, you also got conjunction, kind of a nested. You want to really flatten that out. That's what we want to do. Okay? Let's rewrite this one here to something that's easier to be reused as some hypothesis later. Okay? Equivalent to, we know that red is not equal to green. And I believe that one is in invariance. Let me see, that's in the axiom. You can double check. It's one of the axiom. Okay, so we can rewrite this. MLTL is not equal to red. Also, ILTL is not equal to red. You see what I'm doing here? We used to say it should be equal to green. So it would be equivalent to say it is not equal to red, given that green and red are different. And these are the only two possible values for the traffic lights. Okay? And then we can just do one more. Now we can do De Morgan. So we do De Morgan. So that one there, we're going to do this one here over this. So ML TL equals ret, or IL TL equals ret. So you can see I flip the conjunction to disjunction, right? And then from not equal to equal to, right? That's what I have done. Okay. So this is the final invariant that's to be added, you will see. Okay. So this is our new invariance. All right. So basically, we just don't really want this scenario here to be possible. So we put it as an invariance. Okay. So we're going to put this invariant here back. Okay. So remember the process there. Once you have fixed the invariant, you want to regenerate all the proof obligation related to it. So after adding, so the invariance we have added is this one here, invariant 25. Okay, either of the light is actually red. So think about what we have added is exactly that. Okay, just make it explicit for you. Okay, that's what we have added. And if you try to restate the proof obligation for this one here, the only thing you have added is just this one. That's the new extra hypothesis we have. That's the only thing. Okay. All right, so you can think about the new invariant has now become a new hypothesis. The new invariance has become a new hypothesis. Everything else stayed the same. Okay? So now if we try to prove this one here, it turns out this is now provable. Okay? So what we have is, I kind of highlighted for you. You can see from the beginning, we always got this new invariant as a new hypothesis, right? You can actually keep using it. Okay? I'll let you go over the proof to see how that works. Okay? And then eventually we can get to this thing here that used to be unprovable. But now that we got a new hypothesis, is it going to help? That's the question. It turns out it will help. Okay, I'll go over this with you very quickly. Okay, so what used to be unprovable is right here. But now we are able to add one new hypothesis, which is MLTL equals red, or ILTL equals red. That's what we have. Let's see if this one is now provable. Okay, very quickly. All right, just for this one here, let's now start right here. Okay, just to remind you very quickly, so this is the new invariant we have added. This one here is a new invariance we have added. The new invariance added. Okay, let's now see how we can go ahead and prove this. Okay. And there are actually two possible ways to really discharge one of the branch. I'll give you both hints. Okay? Just to start with, I got some hypothesis that's disjunction. So this is something you did in written test number 2. All right? I'll just put it here. We got OR, disjunction, to the left, right here, of the turnstile. So what should I do if I apply this rule? Should it remain a single sequence, or should I split into two sequences? Split, right? Okay, just good. Just make sure you know. All right, let me just do one branch. The other branch I will leave as exercise for you. So one branch, I'm going to put everything the same, except I'm going to use MLTL being red, right here. Okay, just right here. So I got the green not equal to the red. Also, I got MLTL equals green. And also, I got MLTL equals red. Just the left disjunct. And also, I got ILTL equals, you know what, I don't have enough space, equals green. And then turnstile 1 equals 0. Okay, that's what I have. That's one branch. Okay, you can think about this one here. I'm using just this part, MLTL equals red, just right here, right? The other branch is going to use this hypothesis, okay? And that one there, I will put as exercise for you, just for that branch, okay? Okay, think about it's going to go here, okay? So, exercise. But let's now continue with this branch here and see how we can go ahead, okay? Since you have some equality here, of course, you can experiment a little bit whether you want to use this equality here, or you want to use this equality here, or you want to use this one here. You can try different ones. But I will just try one of them, right here, okay? Let's say I'm going to try this one here. MLTL equals green. Okay, I'm going to select this one here and use the EQLR. Okay, so here I can use the EQLR, which means I'm going to replace every occurrence of MLTL by just green. Okay, that's what I would do. Okay, and then at the same time, so this will be the only occasion you want to write 2 steps in a row. At the same time, I can drop that equality right away by using monotonicity, right? Just to save 1 step. Okay, so let's do a little bit review, a quick preview. I'm going to replace every MLTL by green. MLTL over here is going to be green. So we got green equals red. And that's it. That's the only place I got to replace. All right. So what I will do is I'm going to go green not equal to red. And also this one here, I'm going to drop it. Okay. And also this one here, MLTL will be green equals red. And also ILTL equals green. Turnstile 1 equals 0. Okay. Okay. We're basically there, but there are 2 possible ways for us to go forward, at least 2 possible ways. Okay. I'll give you some hints. You can give it a try. Number 1, you can look at just this one here. Okay. Approach number 1. You can see that's a negation. You can use the not L, which we also spoke about just before the break. Right? If you look at that very quickly, not L is telling us contrapositive. If I got negation over here, what I can do is I can swap that into a go without the negation and put a go as the negated hypothesis, contrapositive, right? So for that one there, you can think about, you simply put green equals red over here and put 1 not equal to 0 right here, right? And now are we done? Yes, green equals red, hypothesis, done. Okay, you can complete that one. Okay, that's approach number 1. Approach number 2 might be even simpler. You can simply go with green equals red. Approach number 2. If you look at green equals red, that one's directly false because they cannot be the same. If you got false as the hypothesis, you basically say false implies anything, right? You can look at a relevant inference rule and prove it. Okay? So that means you will get false hypothesis. Yeah, give it a try on 2 approaches. You can choose either way, right? In case you want to write out the proof in the exam. Either way is okay. All right, today I think we only talk about one thing actually. We try to show that the invariant can be preserved. Apparently it cannot be. So what we did was we tried to introduce a new invariance, and now everything can prove, but there will be some further fixes we have to go with. Okay, any question up to today? Yeah.
So when you say approach 2 using the false hypothesis, do you mean need to combine the green equal red and green not equal to red and say P and not P, that's automatically arithmetic false? And
yeah, for example, you can simply say, I forgot if we got the inference rule. I can double check. For example, you can say that if this is already false, so I can simplify this one to be false using arithmetic, for example, right? In that way, I can say, since I got this one false, and every new line is like a conjunction. So false and anything will just be false. So I basically end up having just a false, turnstile, something, okay? And then I can do another arithmetic to say false implies anything. So this will be provable.
Yeah.
You see what I mean?
Yeah.
Okay, yeah. Okay. Any questions? Diego.
So could you quickly go again over approach number 1?
Of course. This one here, we're saying that, so this one is like a negation. Whenever you got negation in the hypothesis, you can apply contrapositive. You can now swap this guy here to be the goal by taking out the negation. So this will be green equals red. At the same time, you swap the goal to one of the hypotheses by adding negation. That'll be 1 not equal to 0. And green equals red, and also green equals red. You can apply the hypothesis rule. That's done. Okay? All right, so before Thursday, try to see what we have done so far. So I think today we'll finish earlier, and then we're going to talk about another aspect for the refinement. All right, thank you so much. I'll see you on Thursday.